Great. Thank you, everyone, for joining us here today for SWAN Americas Alliance webinar entitled Machine Learning and AI, Enhancing Water Asset Management. We have a great lineup of speakers here today that'll take us through different aspects and perspectives in the water industry concerning machine learning and AI. First, my name is Seth Cutler, and I'll be today's moderator. I'm a principal consultant with Frost & Sullivan, but more importantly for today's webinar, I'm the Americas Alliance lead for events. So it's my pleasure to host you today in this webinar, and I hope to see everyone here participate in future webinars and annual workshops that we put together. As you have questions during the webinar, please do submit those into the chat box on your screen. I'll put those together and we can talk about those at the end with the panel. Quickly to introduce today's speakers. Our first presentation will be led by Jim Cooper, Intelligent Water Lead from Arcadis, and Eric Bindler, Research Director for Digital Water at Bluefield Research. Second is Peter Williams, an independent consultant and former CTO of IBM's Big Green Innovations Unit. And third is Subir Bhattacharjee, CEO of IntelliFlux Controls. Before we get into today's presentations, I just want to take a few more minutes to outline the Alliance and upcoming events. For those of you who are joining us for the first time, the Alliance is here to help drive the smart water and wastewater sector in the Americas. We're a central resource of industry experts that all wish to see this industry thrive. As mentioned, we organize for our members regular workshops and webinars that bring together these different stakeholders throughout North and South America. The strength of the Alliance can really be seen through its diverse membership. Leading utilities and municipalities, solutions vendors and providers, industry stakeholders and research groups really all support the knowledge and valuable activities that we run. And last, we have a great event upcoming at WEFTEC next week. Shirley Bendak, a central lead at SWAN, will be moderating a panel highlighting the strategic outcomes from the SWAN 2019 conference that was held in Miami this spring. The panel is an excellent lineup of industry experts, and they'll do a great job of working with Shirley to communicate key insights from the conference and how those insights impact and can be expanded on with the audience at WEFTEC. So if you'll be at the conference, we really do hope you can join. Certainly let others know about it to join you or for them to go independently if you can't make it. Not to keep you any longer, I do want to pass things off now to Jim and Eric as they take us through and talk about improving utility resilience and affordability with AI. Jim and Eric?
Great, thanks, Seth. So for the next few slides, I'm going to talk about how AI and machine learning can have a positive impact on some of the greatest challenges faced by the water sector, including affordability and resilience. As you can see, the chart on the left is water and sewer rates over the past few years within the US. And the trends cannot continue. There is one recent study that suggested water may not be affordable for up to 36% of households within the next 5 years. There's also, last year, a $67 billion shortfall between the funding requests from the US EPA and the awards of those funding. And we can see that on the chart on the right, where approximately 20% of utilities feel that they are fully able to cover the cost of their services they provide. For these reasons, we feel that adoption of machine learning and AI is really at a tipping point within the water sector. As you can see on the right, we have innovator and early adopter utilities that have implemented AI and machine learning techniques. They are already realizing the benefits and have business cases developed as part of this. And we feel that we're now shifting to the early and late majority adoption of these technologies within the water sector. So we'd like to pose a question on the poll for today's webinar on where you fit, if you have adopted these technologies or not. So that poll will be appearing shortly. In the meantime, I'd like to talk about a few key terms, because as we talk about this advanced technology, it can be confusing, and we want to know, what does it all mean? So when I refer to machine learning, I talk about the ability to improve processing results from experience for a specific need. whereas artificial intelligence is the ability of machines to sense, reason, engage, and learn in a manner that seems intelligent. And finally, collective intelligence is the ability of humans and machines together presenting a far greater intelligence than either could on its own. So whenever I talk about artificial intelligence, someone poses the question, well, AI is going to replace our jobs or replace our workforce, right? And we see it as actually quite the opposite, right? We see that the water sector has always been about people and always will be. And using these advanced technologies enables the workforce to produce far greater results than they have without it. So if I dissect some of the details of what all of this looks at, right, we can start with basic tools and technologies, and then building on that, you get to computational methods such as neural networks or decision trees. Those are then built to develop analytics techniques. And if we think about machine learning, analytics techniques would be things like supervised learning, unsupervised learning, or reinforcement learning. As you continue to build upon that, you can reach artificial intelligence. And often I'm asked, well, what's the difference between artificial intelligence and machine learning? Sometimes people use them interchangeably, right? The key difference is that artificial intelligence is the ability to sense, reason, engage, and learn. Machine learning is one component of that. Finally, we know that we're at a state in AI where it does not match human intelligence capabilities. Often referred to as narrow AI, right? So collective intelligence is engaging the AI with our humans and with our workforce to provide human intelligence capabilities enabled by those advanced technologies. So as you start to navigate current AI challenges, it's important to consider a few things. If you expect that your utility needs perfect data enabled to adopt advanced technologies, you'll probably never adopt those advanced technologies. Obviously, you need data, but perfect data is not required. And today's AI is task-specific, whereas future AI will be enterprise-wide. If we think about using an artificial intelligence technology to identify and predict when you need to replace a pump impeller or a pump motor, you would not use that exact same AI technology to determine which pipes you need to replace in your distribution system. Both are very critical components to asset management, but they cannot be used interchangeably with today's technology. Understand that positive outcomes from AI, just like any other technology adoption, are not always guaranteed, right? This goes into proper planning, developing your business case, and having a successful implementation to achieve those positive outcomes. Finally, the social impacts of AI are rapidly evolving. Things like AI bias and moral and ethical considerations are becoming more prevalent within AI adoption. So I'd like you to think about these 5 questions as you begin to implement AI, or if you are implementing AI and you're looking at the next opportunity for implementation. Does the technology provide a better result, outcome, or business process than your current process? Where is your organizational maturity relative to innovation? Is the tool less complex to implement than other tools with a similar output? If you are using a spreadsheet solver to achieve a result that you can achieve the same result using AI, it probably makes sense just to use the spreadsheet solver. But many times that's not adequate. Can the technology and the data it collects be made transparent across the organization? As we move forward, the goal is to have less silos, not more silos. And finally, can the new tool be easily adopted by the workforce? These are key considerations when you need to frame out and plan for AI implementation. With that, I'm going to turn it over to Eric Bindler, who's going to continue this discussion.
Great, thanks, Jim. So you're going to hear about some really interesting and exciting and much more in-depth examples of how artificial intelligence and machine learning can be applied to the water industry throughout the rest of this webinar. What Jim and I wanted to do for the remainder of our portion of the presentation was just give you a bit of a sense for the breadth of potential applications of AI and machine learning across water. And the impacts really do reach across the entire water cycle, from water supply to treatment, distribution, consumption, be that residential, industrial, commercial consumption, on to wastewater collection, treatment, and then reuse or disposal. But we want to highlight just a couple examples that we think are really illustrative of the potential impact that AI and machine learning can have, particularly around affordability and resilience within the water industry. The first example that I want to highlight is wastewater and stormwater collection networks, and more specifically sewer overflows. Obviously, these are a really significant issue, a really significant challenge from a resilience or an environmental health standpoint. They, particularly for those communities that are under large state or federal consent decrees, they're a very significant challenge from an affordability standpoint as well. Bluefield Research has tracked over 90 federal consent decrees, not counting state level consent decrees, but 91 federal consent decrees between 1998 and 2018. Total estimated compliance cost of about $52 billion. And individual consent decree programs can run as much as $3, $4, even $5 billion, which obviously imposes a really significant financial burden on utilities and on their ratepayers. What we found, though, is that utilities that have worked with solution providers to implement artificial intelligence and machine learning have been able to meet their overflow reduction requirements by, for as much as 5 to 10% of the cost of traditional large-scale infrastructure programs. And they do this in several ways. One of the key kind of dimensions is gathering robust data from throughout the pipe network, from throughout the collection system, on flow and on level, combining that with real-time, for example, weather data or meteorological data, to really start to enable a machine learning system to really start to learn how that specific sewer system will behave under specific conditions, whether that be in a wet weather event or other types of conditions, and essentially optimize the existing storage capacity of that pipe network, rather than needing to build expensive new storage tanks, for example. Actually optimize and make the best use of the existing capacity by either automatically opening and closing gates and valves, or making recommendations to system operators to make sure that they're really operating that system in the most efficient way, making use of all the existing capacity and reducing overflows. Another really great example is in treatment plant operations, and you're going to hear a good deal more about this later in the webinar, so I won't touch on it for too long. But essentially, looking historically at Congressional Budget Office data for water industry capital versus operating expenditures, we see that over the past few decades, OpEx has really skyrocketed relative to CapEx. About $80 billion per year for the past few years of water utility operating expenditure. There are a number of different ways that artificial intelligence and machine learning can be applied to help utilities really reduce and optimize their operating expenditures, whether that's at the treatment plant level, monitoring and predicting water quality of incoming water to enable more kind of precise and pinpointed application of chemical dosing, for example, or monitoring and eventually learning and being able to predict and forecast demand, comparing that against spot price of electricity and fluctuations in energy prices to optimize pumping. And then finally, monitoring asset health, monitoring asset performance to ensure that when an asset starts to deteriorate, when it starts to operate less efficiently or at a lower capacity than designed, that the system is able to, the algorithms within the machine learning system are able to recommend maintenance interventions to make sure that those issues can be addressed before they result in a large-scale failure of that asset. And then finally, one application that maybe we don't think about quite as often, but I think it's also really illustrative of the kind of breadth of what artificial intelligence and machine learning can do for the water industry and for water industry customers, is within the level of individual homes. So this is some information from the Insurance Information Institute suggesting that Within the U.S., water damage and freezing are the single largest contributor to homeowners insurance losses. So on average, about 31%, 30 to 31% of total homeowners insurance losses are attributed to water damage and to leakage. And individual events, individual claims typically run around $10,000 per household. And the average U.S. household loses about 10,000 gallons per year of water through undetected leaks. What we're seeing is a number of vendors coming out with solutions, kind of piggybacking off of the broader smart home movement with Alexa, with Amazon Alexa, and with Nest thermostats and Ring doorbells. Essentially, smart home leak detection devices that can monitor and eventually start to learn the kind of common behavior, the common water consumption trends of individual households, and then detect when patterns start to deviate from those trends. So whether that's a small scale leak that's developed or a large scale pipe break, these systems can automatically turn off water supply to the house to prevent any further leak, any further damage, and notify the household that something has gone wrong. In many cases, these devices are geared more towards individual homeowners, but we are seeing some utilities start to actually partner with providers of these devices to, for example, offer rebates to their ratepayers, to their customers, to put these devices on and really protect them from water loss and from both from a resilience standpoint, the unnecessary water loss associated with that and wasted water associated with that, but also the damage that ratepayers are responsible for or are faced with, from undetected leaks. And so with that, we thank you for your time. We're going to turn it over to Dr. Peter Williams to explore this topic further.
Great. Thanks, Jim and Eric. Peter, 1 second. Just for those who joined us a little late, as you do have questions, feel free to insert those into the chat box, and I will manage those at the end of the presentation for the Q&A. Thanks. Peter?
Very good. Thank you. And I think some of the themes that you've just heard are going to be reprised in what I have to say as well. So artificial intelligence, as this webinar is evidence of, is hot right now. All of those quotes on the right-hand side are from the last couple of months in various journals that I was reading. But the interesting thing about AI is it's not actually new. In water. It's certainly seen as the next technological step on the way to a digital water agency. It's not new. It's been around in some form or other for at least 10 years in areas like leak detection, pipe failure prediction, pump optimization, and so on. And it's absolutely not a silver bullet. So what I thought it would be useful to do would be to try to present somewhat of a devil's advocate view of AI. I'm an absolute believer in AI, but I'm going to spend the next few slides trying to persuade you that I'm not. Because I think that's a useful thing to do. The first point I guess I'd make from a devil's advocate perspective, the technology is evolving so fast that the industry is actually unstable right now. Even by the standards of the last 25 years, the rate of progress in AI, as measured by things like the number of patents and the growth in new styles of AI, new techniques, new tools, and so forth, is absolutely astounding. What that actually means is that competitive advantage for any given vendor that's majoring in AI is probably going to last for about 20 minutes. That's good in a sense. The prices will come down, and if you're the sort of kid in a candy store mentality, there's going to be plenty of new options for people to try. It's also bad because your utilities AI strategy may not weather well, may not look good with age. And one of your strategically chosen AI vendors may have disappeared or been taken over just when you need them. What it also means is that if you're a vendor in this space, you need something a lot more than just AI alone as your secret sauce, or you're not going to be there for very long. And it also means that utilities who are buying AI need a better idea than just buying AI for its own sake. As the previous presentation made very clear, you need to have some clear purpose in mind, and you need to understand that AI is in fact an improvement over what can be done today. Second aspect of AI is a lot of the benefits that are claimed for it are not actually AI benefits when it really comes to it. A great example is a company that I was working with recently, make an excellent product for optimizing the operation of water treatment plants. They specifically address tough to predict influent volumes and influent quality fluctuations in those. They specifically address the issue of operators effectively just guessing cycle times and chemical doses based on experience rather than on science. It's got a proven track record of generating major savings from reduced energy, reduced labor, and reduced chemicals, exactly as we just heard. So you might think strike one for AI. But in fact, when you look under the covers of this product, and they don't, to be fair to the vendors, they don't make huge claims for AI in it, but it's just an example that really caught my eye. What actually drives this product is not AI at all. It's a chemical physics model of each of the unit operations in a water treatment plant. They've literally modeled the chemical equations that describe the processes going on at each stage of water treatment. It took them some number of years to do that. But what they have is a deterministic, not an AI, but a deterministic model that actually captures the operations of most water treatment plants. And in any given application of their model, they can get 85% of the way there with this deterministic model. They then just use a neural network to calibrate the model to the particular water treatment plant that's actually using it. So I leave the open question with you. Is that actually a strike for AI, or is it for good old-fashioned chemical engineering? It's certainly worthy of thought, because it does raise the issue of, well, how far can I get before I actually resort to AI? Especially as, from a devil's advocacy point of view, AI may actually be just a better mousetrap. We hear a lot about artificial intelligence in leak detection. Well, you can detect a great many leaks with current techniques that don't necessarily use AI. And actually, at a certain point, economics applies. Once you've detected the leak, you've still got to dig up the street and you've got to fix the leak. That's expensive. AI is not going to fix that part of the problem. Therefore, the benefit upside for AI in leak detection may not be as great as you might think. Similarly, if you are using AI to optimize water quality, once you can consistently and reliably meet statutory requirements for water quality levels, how much actual further upside is there in artificial intelligence? This is a question you may well want to ask. If you're only meeting those requirements very inefficiently, there may well be some upside, but equally the upside may not be as much as you might think. Equally, you may find that the benefits that you're thinking to apply from AI have been preempted by an earlier tool. And as an example, from my own days in IBM, IBM was using Maximo back in 2010 to predict which pipes are at risk of breaking next year. And also, incidentally, to predict which roads are at risk of breaking up next year as well. And they were using statistical clustering and machine learning, which you would think of as sort of precursors or early forms of AI. And they were using it very effectively, 18% reduction in cost at the same level of reliability. What is any new application of AI going to add over and above this level of performance, which is available already? So there just needs to be some thought of, hey, wait a minute, are we just buying a better mousetrap? Especially when the water sector doesn't have a great record of using the mousetraps that are already there. The speed of technology adoption in the water sector is notoriously slow. Another point to make about AI is that actually just be very clear what you're buying, because the value of AI may not actually be in the AI part. The value of AI may be actually enforcing the integration of data between different functional silos. And we certainly see this in some of the central event management products that are out there from the likes of Takadu and Trimble and such. They do use AI, but actually, if you really look at it, their real value lies in creating the proverbial one version of the truth that all of the different functional silos, the operators, the maintainers, the planners, the financiers and so on inside a water utility can buy into. The real value lies in enabling them to collaborate without actually having to necessarily surrender control of their own data to some other functional silo. So the actual, what you're getting with AI may not be what you think you're getting. It may be valuable, but it may not actually be the AI that's delivering the result that you really need. A further and final example of devil's advocacy for AI is the fact that it is, in many cases, somewhat of a black box technique. It's certainly absolutely dependent on data selection and data quality, as we just heard about growing concerns about bias and so on and so forth. With AI, it's garbage in, garbage out, as it always was with computing, but absolutely on steroids. But more seriously than that, many public systems, infrastructure systems, utility systems are distributing a social good. Equally, some of them are safety critical. If you're using computational techniques that produce results where you can't actually see why it has produced those results, where you may in fact have some kind of accountability requirement and so forth, AI might very well not be a good match for what you're trying to do at all, because it may not allow you to assess the safety criticality of something. It may not allow you to demonstrate why the system has been operated in the manner that it has. It also says that successful and less risky AI applications are going to tend to be incremental add-ons to current practice. So I guess the watchword in this would then would tend to be kind of beware of moonshots. I was saying earlier in the example about the water treatment plants that the useful application of AI was in fact only a relatively small part of the value. That might very well be okay in the context of applying AI in a public service. Which brings me on to my final slide, really, which is just my own thoughts as to how AI might most usefully be applied. Just picking up on some of the themes about data integration and so forth. Perhaps actually the key to AI is a different technology altogether, which is digital twins. Digital twins integrate core layers of asset data, and I've given some examples there, the blue bars in the diagram, whether it's GIS, asset management, the hydraulic model, SCADA system and PLCs, whether it's other IoT devices, maybe it's external data layers as well, maybe it's providing an event management capability over the top of that. The point about the digital twin is it pre-integrates all of those layers. That allows you to conceive of AIs as effectively just coming up with new uses for data that you have already integrated. Certainly when you talk to water utilities, many of them will admit, you know, we really do need to get round to this sort of data integration aspect. We really do need to think about it if we're going to become a digital utility. So I'm encountering a climate in the work that I do where at least forward-thinking utilities are saying, you know, we really have to bite this bullet. The point being that once you've bitten it, you can then implement AIs much more easily and much more satisfactorily. So, for example, if you are using AIs to optimize energy consumption, you're going to be using the same asset data, SCADA data, and hydraulic data as you would have done for predictive maintenance. If you are going to use if you want to use AIs for leak detection, you're probably going to be using the same hydraulic and SCADA data that you would have integrated for energy optimization. So my point being that once you've created this integrated set of data layers in the digital twin, applying AIs becomes much more of an incremental, much less of a risky bet as you move forward. That's as much as I had to say on AI. I'll be very happy, obviously, in the format of this webinar to take any questions that people have. But right now, let me hand on to Subir. Thank you very much.
Thank you very much, Peter. And what a beautiful segue into what I'll be going to speak about. I'll just narrate the experiential learning that our company went through with an installation in South Korea, which pertained to optimization of a membrane filtration system at a 10,000 cubic meters per day plant using some element of artificial intelligence, some element of digital twin, and a machine learning driven automation software, IntelliFlux, which resulted in increase in production, lowering OPEX, and a few sustainability and reliability benefits of the plant. Hopefully, the brief narration will show you what the experience was. I'm Subir Bhattacharjee, CEO of IntelliFlux Controls. The profile of this case study is as follows. Our customer is a water reuse system and service provider. You generally refer to them as design, build, operate companies who owns multiple assets in South Korea ranging from 10,000 to 30,000 cubic meters per day. The specific plant we installed in IntelliFlux last year in June was a plant in Incheon near Seoul, which treats municipal secondary treated wastewater using a combination of submerged hollow fiber membrane bioreactors followed by a reverse osmosis system. And it produces the treated water and supplies it to a steel plant complex nearby. The challenge that this plant faced is inconsistent operation and upsets caused by influent quality variations. In summary, when we discussed with the customer and various stakeholders within the customer's company, the overall message was influent quality variations are causing margin erosion in that project over the lifetime of the plant, and it's getting progressively worse as the plant is aging. And when we talked to different stakeholders, they turned up all as multiple OPEX consequences, which were described differently by various stakeholders, like lower production, lower yield, more waste, increased plant downtime, increased labor and maintenance, frequent cleaning requiring a lot of operator intervention, higher energy consumption, reduced component life, and frequent component replacement. Now, of course, we did homework with the customer to figure out what else did they try during the previous 5 years of the operation of this plant. And it ranged from trying to figure out what capacity enhancement to meet the shortfall or any kind of derating would require. The essential message was it would be CapEx intensive, and doing midway of a project is sometimes not a very good business decision. They, of course, resorted to aggressive maintenance, which requires adopting fail-safe maintenance models, continuous plant monitoring. Basically, plant monitoring was intensified. However, no automation was implemented to meet up with that. Of course, involving more labor and implementing these incurs higher OPEX. The third part, which is very common in water treatment business, is the existing technology is not suitable, and so we have to install new technology. And this company wanted to install something for their intake water, but that proved to be too CapEx intensive. There were various bootstraps that were used to manage the total cost of water, such as managing the vendor chain more aggressively. They led to inconsistent outcomes and stressful supply chain relationships. And finally, what the company was basically resigned to was plan for the depreciation, margin reduction, and increasing OPEX over the lifetime of the plant. This is the point when in 2017 we did a pilot on a small plant with the company, and they adopted in their stage gating process to the next get of putting it on one of their working 10,000 cubic meters per day production plant. We primarily managed the membrane filtration MBR systems, ultrafiltration unit, but I'll come to that details shortly. But let me discuss what we proposed to them. So we proposed to them our solution IntelliFlux, which was positioned as a software which acts as a plant operating system, which could be customized for their plant. It is a combination of software and an edge control device, which we will place in the control room of the plant. And it would provide autonomous control that is capable of intelligently adjusting to the process variations. And it would provide an element of operator assistance and decision support with live monitoring and reporting. The essential sales pitch for us was that it will convert the conventionally operated plant to a smart plant. The key features of IntelliFlux that we presented to the customer and that was attractive to them was it will take the philosophy of an operator of the plant who will come and is given an SOP or standard operating procedure to start operating the plant. And as that operator learns and gains experience about the plant, it basically that operator is able to deal with various types of predictive aspects of how to manage downtime, how to manage the data and various other aspects. So the features in IntelliFlux was there was an element of machine learning based optimization. We provided the automation part, which means we were managing the set points and responding to upsets in real time. So we implemented real-time decision automation. The installation had to be plant hardware agnostic and a retrofit solution, which implied that we won't be adding any sensors or additional hardware. The premise was an operator gets to the plant and gets the plant as it is to operate. So IntelliFlux has to do that. And finally, we of course had to crunch numbers and get temporal resolution of data. So we used a very interesting client-server based smart data framework where we relegated different types of tasks based on their time value or what's the immediacy quotients. How we delivered these results, I'll be very brief, but this is perhaps a little pedagogical. But what IntelliFlux incorporates is a ground-up implementation of the Industry 4.0 digitalization stack in a unique client-server package that enables overnight transformation of an existing process plant to a smart plant. How we do it, there are 4 pillars of that delivery process. We focus on the process automation. Here we use system engineering and adaptive process control tools and paradigms that are used for 50 years in plant management. Conventionally, this should be ideally a subset of what you call the digital twin technology. We needed to take autonomous decision-making and optimization features, and so those features were embedded in the software. This embeds some element of very deterministic process modeling, as well as some elements of machine learning and artificial intelligence. The third part was we implement the IoT, the advanced analytics and artificial intelligence and machine learning tools through the edge computing device, which allows us to be a little more timely, so the system responds in near real time to any influent quality fluctuations. And finally, we provide a unified platform for customized implementation of a digitalization framework for the specific processes and the plants so that every stakeholder sees the same truth. I hope you heard about all these elements in the previous presentation. To just quickly go over the Industry 4 design principles that are embedded in the product, we embed the 4 pillars of interoperability of different components of the plant's technologies, as well as the human element that is present there through a combination of data sharing, sensors, actuators that are correlated using a single interface. So we have a much broader optimization phase space. We use the transparency for the plant operators and engineers by providing the mapping of how the process is operating by comparing it constantly against the digital copy of the physical system or the plant. So we are mapping the progress of the plant's operation against its digital twin. The third element is decision support, which everybody understands from the products that is provided. We provide dashboards, correlations, analysis, some predictive, some historical, that allows the operators and stakeholders better visualization of how the plant is operating. And the final step where we think we are a little differentiated is we take the liability of automating some of the processes. The liability's extent is very small in our mind. We know the phase space in which the operator gets to change set points, and we use that phase space to change the set points and allows us to respond to any condition without the operator being constantly present in that system to monitor the system. So to get back into our case study, here is a snapshot of how the installation was done. The plant is shown on the left panel photograph. The middle panel shows the control panel, and tucked at the bottom on the floor, right side of that control panel, is a small box, which is enlarged on the right-hand side photograph, which is basically our edge control device. It is simply connected to the PLC and the network, the SCADA network, and it basically collects data and sends instructions to the PLC. The software configuration, the patch coding of the PLC, and all of it can be customized for the plant once you know the process information in about 2 weeks. There was no additional sensor or there was no downtime other than to reboot the PLC when you put the new program, and it could be tucked in during a natural downtime or a shutdown for maintenance. And the ECD, once you install, it starts immediately learning, gathering data, and correlating the data and providing the plant optimization framework, which it learns within the next 7 to 14 to 28 days, depending on the frequency of observations of certain kind. Jumping to the outcomes of this study, since this plant has been operating for more than a year and a quarter, we have been monitoring it very closely. More than us, the customer has been monitoring the progress, and we aggregate the results daily, weekly, monthly, quarterly, and yearly. And during the last year, these were the average results they got out of the membrane filtration plant with IntelliFlux compared to the baseline operation, which was based on previous 3 years of operation of the plant. So for energy, we reduced the energy consumption of the plant by about 34% on average. The disposal volume was reduced by 30%, which was a cost center, and that basically was reduced. The production on average from the membrane filtration system was increased by 3%, which is quite a bit for a 10,000 cubic meter per day plant, 300 cubic meters per day. And the membrane life was a very interesting observation. It formed a part of the depreciation, and we arrested the rate of that depreciation during the last year. So their projected membrane life is now increased by about 20%. So to summarize, this system has been operational since June 2018. In this, on top of the above metrics or KPIs, we provided regular operator alarms for any kind of anomaly like a pump shutdown or a tank not being filled up to the proper extent, or a lowering of a dose of a chemical because the chemical's original dose was not correct or concentration was not correct, to managing the system through upsets. We auto-generated reports for the operators, and the operators and everyone in the management loves us for giving them reports by the rote, which basically did not happen earlier on such a regular basis. And they calculated the energy savings of the plant and projected that the ROI for the product would be in about 5 years of time, which was news to us, but it was interesting to know that it fit the customer profile based on that. It was only based on energy. The customer, of course, plans to expand it to their other plants, and they have actually become our regional distributor of the product in that market. Here is a customer testimonial in the slide on the right-hand side, but I would like to focus first on what led to that testimonial after about a month and a half. So I tracked two values of daily averages on the two graphs in the left panel. The top is a disposal volume, and the bottom is the UF recovery, which shows the yield of the plant. And in the black bars, you are seeing what happened before June 25th when we installed and turned on IntelliFlux, and what was happening since then in the red on the right-hand side. And you could see very clearly that there was a distinct difference in the patterns that evolved daily in terms of reduction in disposal volume and increase in UF recovery. And this sold the product to the customer, because in any of these applications with a service model, our biggest challenge is that we have to remain stuck to the customer and be of use to them. So with that, I hope I have given you a case study that shows that all of the concepts that were discussed in the earlier two presentations, we have a minimum viable implementation of that stack that we are trying our best to productize and provide our customers at a good price point. If you have any questions, I'll be very happy to answer those. Thank you very much.
Wonderful. Thank you, Subir, Peter, Jim, and Eric. What I'd like to do now is just open the forum up to questions. If anyone from the audience has additional questions, feel free to submit those into the chat box. Where I thought we could start was actually looking at the poll that we pushed out at the start of the webinar. So we asked the audience who is currently using AI or machine learning to help manage their water or wastewater networks. What we had with that, the numbers did bounce around a little bit, but where we ended was 46% said yes and 54% said no. I'm just wondering from the panel here, does that offer any maybe implications or generate thoughts from you on the current journey for utilities along artificial intelligence machine learning? Are there any comments, or maybe start with Eric or Jim?
Sure. This is Jim. I can provide some thoughts. So I think, as expected, right, these results are showing a higher percentage of folks adopting AI and machine learning than probably the overall sector, right? We tend to focus in on the things that we are currently doing. So we see that 46% are currently using these technologies, which is great. And think that it's definitely out there. It's also good to hear that there are folks that half the group is not currently using them and they're interested. So yeah, it's a good blend. But like I said, probably a bit more on the yes percentage here than an overall representation.
Thanks, Jim. Any other comments, or should we move to the next question? Okay. So one question, maybe towards you, Peter. Thinking about digital twins, I mean, there's a lot of thinking that it's a heavy lift. How soon do you think digital twins are really going to start to enter the mainstream and become much more common, not just in discussion, but actually on the ground?
I suspect actually they're going to become, they are indeed a heavy lift, but I suspect they're going to become mainstream sooner than some folks might think. If you look at some of the central event management tools that like the two that I mentioned, for example, they embody elements of a digital twin right now. It's a bit like kind of AI. They've been doing stuff that you would have to do to create a digital twin for some years. They just didn't call it that. But equally, if you then look at the quality of some of the digital twin tool sets that are available but aren't yet used in the water sector, whether you're talking about the Microsoft Azure tool set, or whether you're talking about SIBO, or indeed whether you're talking about City Zenith, I hazard a guess that it's going to come to the kind of idea is going to come to the water sector sooner than you might think. Also, if you look at the tools that are available, the so-called process twin tools that are available to help design wastewater treatment processes, water treatment processes, and so forth, the integration between those and asset management, or the integration between those and optimization, is effectively an instance of digital twinning right there. So my contention will be that it's going to happen in a number of different guises, in a number of different ways, probably sooner than you might think.
Great, thanks, Peter. And actually, we've had a follow-up question to that as well. And just, I guess, from a more of a practical perspective, where should people start when it comes to the implementation of digital twins?
Yeah, that's always the $64,000 question. Probably start with any two, the data from any two silos that you would like to collaborate better. One of the advantages of a digital twin is it allows you to pull off a bit of organizational alchemy, because it allows the asset maintainers, it allows the planners, it allows the operators to contribute their data to the digital twin and get back something bigger than they gave, without anybody actually giving up control of their data in the first place. So, for example, if you wanted to implement a continuous comparison between a continuously running hydraulic model on the one hand and a SCADA system on the other, so that you can continuously compare what the hydraulic model says should be happening in the water system and what the SCADA system says actually is happening, that might be a good place to start. Or if you wanted to engage in something like energy or pump optimization, you'd probably want to integrate SCADA and asset management data along with the the geographical layer, if you didn't already have that, to allow you to think about asset dispositions, maintenance patterns, predicting failure in those assets, assessing pumps against the manufacturer's curve, and so on. So pick a problem and solve that, and then go pick the next problem and add on to what you've already solved. So try to do it sort of stepwise rather than trying to do it as a single big bang. I used to work for IBM and Accenture and companies like that. We really love big bangs. We make a lot of money out of them. But if you can do it incrementally, it's a much lower risk.
Thanks, Peter. And I think here's one to the group as well that was submitted. And just talking about The Hill, the publication recently ran an online article on Moneyball, opportunity with artificial intelligence on infrastructure. Given the current state of industry and labor shortage and the value of smart sensors to watch over systems and automate operations, do you think we could achieve a larger savings with smart sensors that reduce labor costs and mitigate risks, etc.? I know SWAN members looking at OSI Soft and SmartCover have documented savings above 90% by transitioning from manual to AI-driven operations. What do you see as the Moneyball opportunity, and how do we promote this?
I'll go first if you like, because I've actually...
Sure.
I think one, and it might be slightly off to one side in some people's minds, is the whole area of disaster resilience. I was talking to a water utility in Florida. I was working with them a little while back, and their prior experience of dealing with a major hurricane dated all the way back to Hurricane Andrew of 1982 or 72, whenever it was. The people that had dealt with it at the time are now all retiring. And nobody really wrote down what they did to get that utility up and running after that major hurricane. It was all there in people's heads. And of course, as they retire, that institutional knowledge is walking out the door. It's leaving the organization. You could easily come up with a cognitive AI tool that captured that knowledge and provided decision support for hurricane restoration, for restoring a water service after a hurricane. That might be, for my money, looking at the impacts of climate change, looking at the impact of sea level rise, and looking at the growing concern that many water utilities have around things like climate resilience. That actually could be a Moneyball application for AI, simply capturing the institutional knowledge represented in the heads of the people who are about to retire. And by the way, that is a worldwide problem too. I've encountered exactly the same thing in Vietnam. I've encountered exactly the same thing in Australia.
Perfect, thanks. And wondering, either maybe Eric or Subir, do you have any thoughts on what might be this Moneyball opportunity looking forward?
I'll first defer to Eric if he is there.
Sure, yeah. I'm not familiar with the article. It sounds interesting. I'll definitely check that out. I mean, I think, I don't know, just broadly, some of the other types of applications that, that we're tracking at Bluefield that we think are really interesting would be on the water quality front. Certainly, I think that market has kind of grown in fits and starts in the US. Obviously, there was a lot of attention around particularly online water quality monitoring after 9/11 and just kind of broader moves towards security in the infrastructure space. But one area that, I think we're seeing some interesting product developments, for example, is in essentially, combining the power of AI and machine learning in terms of being able to detect and be able to identify different types of contaminants, kind of looking at real-time water quality data and comparing that against databases of different types of contaminant footprints, for example, and being able to identify really what's happening and what's coming in, what's traveling through the pipe network, what's in the water supply, and being able to take action. I mean, I think I've seen there've been some interesting product releases in the past year or so. Combining that type of detection and identification of different types of pollutants with automated treatment processes. For example, being able to turn on aerators and storage tanks when activity consistent with disinfectant byproduct potential is kind of detected. And so I think that's another really interesting example. It may not be the same level of Moneyball as I think what Peter was talking about, and it may take a little bit longer for that particular area to develop, but I think it's another interesting one to keep an eye on.
Thank you. I mean, I don't have much to add on that because whenever we take a top-down approach on any of these, especially in water, I always am reminded of a statement I've heard over and over again. Water is the biggest global fragmented market that we have seen. And our bottom-up journey of going customer to customer and trying to sell this product in different markets, different landscapes, has just shown us that the penetrating this market based on value proposition is the lowest common denominator. So you have to make an economic benefit for the customer. And with water's price structure in different markets differently, and the cost of labor, the attrition of labor, the cost of putting the technology in, whether it is a PPP project or a government-run project, all of these factors are such big variables that whenever I have gone with a predefined theoretical architecture and attacked a specific market, I have often been surprised than not. Energy is extremely important in South Korea, great news, but I have gone to US municipalities and I have been told it won't be useful. So the whole idea is that cost of energy itself is not going to sell AI. And at the end, it has to be the customer's value proposition about what will be adopted. But you are just hearing a bottom-up, ground-up approach that we are taking, and it may not have a widespread relevance.
May I add to that?
Yeah, please.
One area where it may apply, however, would be as some cities are now trying to do under the guise of smart cities, is to effectively use the city's water supply as a giant battery for demand response. And where water pumping activity is impinged upon by neighborhood microgrids and that kind of thing. Using AI to enable the electricity system and the water system to be co-optimized with each other, while still respecting, obviously, the operational parameters of the water treatment and the water pumping process on the one hand and the energy grid on the other. I think that, looking down the track, is going to be a huge area for AI, simply because it's too complicated for individuals to be able to deal with.
Yes, I like the premise, and especially with pumped hydro, managing cost of deregulated electricity was one of the earlier smart energy framework. This is an extension of that to the water energy nexus. I'm seeing these types of projects becoming important in places like Cape Town, where we have a couple of installations. They are excellent architectures to actually draw attention. However, at the end, the customer wants a value-based solution. And I have often been, like, if I go too heavy with AI, it becomes something like a magic wand with which we are presenting the problem solution approach. So in that case, I would take the lessons that I heard from Peter's talk, which is be a little skeptic and present an appropriate solution that is case specific at that place. Otherwise, we run the risk of overselling a concept, and the customer comes in with a predefined notion of what this will do, and we end up, the small companies who are starting it out, they end up trying to deliver a very half-baked product, fulfill the expectation of a customer who has heard the full rhetoric. My 2 cents.
Great, thanks. I know we're pushing towards the top of the hour, but I'm hoping to get through 2 more questions here. A first one to the panel is talking about how the examples for AI in water that a lot of people are hearing at the moment are centered around utilities, facilities, sometimes in residential areas. This makes sense from an economic point of view, or an economic incentive perspective, and because the data exists in large amounts. But has anyone come across AI being used at the basin or watershed level?
Sure. So this is Jim. I can take that. Absolutely the case. It is being discussed at the basin and watershed level as well. There's a couple key utilities out there that are doing this. I won't name them, but be happy to talk about that offline. But one of the initiatives where AI can have a significant impact is as we think about one water, right? And we bring in reuse and we bring in essentially the one water movement tied to smart cities, there's quite a number of instances of AI and machine learning that's implemented as associated with that.
I'll give you a couple more examples too from my own IBM days, 5 and in some cases 7 or 8 years ago. One is Lake George, New York, huge project to monitor and predict the quality of water in Lake George and the dispersion of pollution plumes within Lake George. And the second is the Grand River watershed in Ontario, Canada. So those are examples of AI being deployed at the watershed scale.
Perfect. And let's end on this question here as well. I heard during the presentation that it is not. Actually, one second. I think that moved. I heard during the presentation that it is not necessary to have perfect data to start looking at using AI and machine learning. That being said, my concern is that the rewards of AI and machine learning are limited by the quality of data that you have, and it makes someone like me hesitant to move forward with any advanced intelligence with this thought in my mind. What would you say to people like me who are hesitant to move forward due to this issue?
Sure, well, I'll take that. I think that was a reference to my slide, but others may have thoughts too. First is, if you need to wait until you have adequate data, like I mentioned, then you'll probably be waiting and miss significant value. There's absolutely a balance between the value you're going to get out of the current quality of your data versus losing that value and waiting to implement something much later during time, right? So it really depends on the instance. I've seen utilities adopt AI when they did not have enough data to do so, and they get results and go with it, and they probably shouldn't have, right? And there's some that have more than sufficient data when they don't think that they do. So it really depends on the application. I mean, my advice would be talk to the experts, right? Talk to the folks that are doing this and really get an understanding of what data you have, regardless of if you're using AI or not, or machine learning or not. What data is the base level of data that you need to be able to measure, monitor, and optimize what you have.
Very interesting work that's been done in a utility in Australia to try to figure out, using their AI-based leak detection algorithms, how few sensors they still need to be able to produce worthwhile outcomes. And the answer is you can actually reduce the number of sensors by quite a lot, and you still get something that's 85 or 90% as effective as the original solution. I don't recall the exact numbers, but it's a systematic study. They basically knock out or disconnect one hydrophone, one microphone at a time, and they see what that does to the quality of their predictions. And it seems to indicate that actually a reduced level of data would probably have been sufficient to produce usable outcomes in their case.
Wonderful. Well, thank you to the panel. I know we pushed a little bit over the hour, so I do appreciate everyone staying with us and really listening into this discussion. It's been great. So thanks again. The recording of this presentation will be up on the archive on the SWAN website, so do feel free to check that out later or pass that on to colleagues of yours that would be interested. Please do reach out in future if you have any questions. We can always help you with that afterwards. But in the meantime, thank you very much to the panel, to Sabir, Peter, Jim, and Eric. We really appreciate your time. Thank you.
Thank you, Seth, for all of your hard work.
Absolutely. Thank you.
Thank you. Bye-bye, everyone.